Welcome to This Explainer. Right now, all across the globe, there's this quiet but absolutely fierce acceleration happening. We're officially moving out of that old era of simple robotic arms just swinging back and forth in predictable, controlled factories, and we're stepping right into the age of embodied intelligence. We are talking about the global humanoid robot race. It's a space where AI minds, mechanical muscles, and massive digital platforms are colliding at a speed we've honestly never seen before. It is highly realistic, it's unfolding way faster than anyone anticipated, and today we're going to break the whole thing down. Okay, think about this question for a second. We've all seen what artificial intelligence can do on a screen, right? It's incredible. But what happens when you take that raw digital reasoning power, you give it a physical body, and then you equip it with not just one, but two mechanical brains? How do we actually bridge that massive gap between flawless, clean digital intelligence and our really messy, highly unpredictable real world? Okay, let's dive into this. To understand the new humanoid race, we're going to take a journey across three major hubs: China's dual-brain architecture, Vietnam's expanding ecosystem, and the US's foundational platforms.
Starting off with Section 2, JAKA Pi and the concept of the split brain.
Our first stop is Shanghai. JAKA Robotics just unveiled a new humanoid named Pi, and it is highly compact. Just look at these specs. Pi isn't one of those massive, clunky, intimidating machines you usually see dominating the headlines. It stands at just 4 feet tall and weighs a lean 92 pounds. But don't let the size fool you, because it's incredibly capable, packing 27 degrees of freedom. JAKA basically pulled this off by developing new integrated joint modules that are 15 to 27% smaller than their older stuff. So it's a lighter, much cleaner body. The knee joints still deliver serious torque, about 88.5 pound-feet for highly stable walking, and each arm can carry around 6.5 pounds. This isn't just some flashy walking demo. It's a platform built specifically for real-world interaction, physical manipulation, and intense research. Now, what's really interesting about this slide is the architecture they've built on Intel's computing platform. JAKA has effectively created a split brain. They're leaning heavily into a biological metaphor here, and it makes total sense. On one side, you've got the cerebrum. This is the thinker. It handles high-level intelligence, AI reasoning, vision, large language models, basically figuring out what the robot is actually supposed to do. On the exact opposite side is the cerebellum. This handles real-time movement through an EtherCAT network with millisecond-level latency. Why separate them? Because humanoids absolutely desperately need both to function. If you tell Pi to do something, the cerebrum understands you and plans it out. But it's that cerebellum that simultaneously keeps the robot from falling over and actually executes the physical movements without crashing into a wall. And this dual brain system is a huge evolution for JAKA. They were founded back in 2015, and they started out with industrial collaborative robots, cobots. You can see their whole progression right here. The Zoo series for packaging, the Pro series, which was built for harsh, dusty, wet environments, and the S series with really advanced force sensing. Now, with Pi joining their K series humanoid lineup, they're taking large language models and merging them directly with real-world physical force control. And guys, this isn't just theoretical anymore. Chinese robotics are already advancing into real-world logistics as we speak, like automated parcel sorting in Guangzhou. They're aggressively breaking out of the factory and moving into everyday environments. Which brings us to Section 3, Vietnam's robotic ecosystem. Let's shift our cinematic journey south to Vietnam. We are looking at a massive, and I mean massive, double entry into the humanoid space by the Vingroup ecosystem. Look at this direct contrast. Vingroup isn't just satisfied building one robot. They are aggressively attacking two completely different markets at the exact same time through two different subsidiaries. On the left, we've got Dino from Vin Dynamics. This one targets unpredictable public spaces, urban security, commercial service, household assistance. But then on the right, you have VRH3 from Vin Robotics. This one is entirely built for strict industrial precision, material handling, and complex payloads. It's packed with 31 actuators and dual onboard edge computers. Think about it. Building a robot for a tightly controlled warehouse is incredibly hard. But building one for a messy, unpredictable living room? That's arguably even harder. And Vingroup is going after both. And they aren't just leaving these in the lab. They're actively stress testing them. Take Dino, for example. It was recently deployed as an autonomous robotic guide at the Vin Pearl Safari Phuquoc. Picture this for a second. It is completely outside the pristine, clean laboratory. Dino is out there operating in outdoor conditions, dealing with massive crowds of people, unpredictable lighting, loud noises, and of course, totally unexpected human behavior. It was using multilingual speech and real-time environmental awareness to actually guide real visitors. This is literally the ultimate crucible for a service robot. If you can prove it handles the chaotic reality of a safari park, that shows a level of situational awareness that you just cannot replicate in a lab. So how do they actually power all this? Let's zoom in on the muscle system. Vin Dynamics developed this VDM80 actuator joint. It's incredibly compact, it weighs less than a kilogram, but it spins at 235 RPM with an expected operational life of over 10,000 hours. And they take this super durable shoulder and leg muscle and pair it with a very delicate, human-like robotic hand. We're talking 11 moving joints, 6 active degrees of freedom, and integrated force sensors for precise handling. Because Vin Group is vertically integrating all of this in-house, the muscles, the hands, the entire mechanical architecture, it gives them a massive long-term advantage when it comes to fine-tuning energy use and balance for future iterations. And speaking of vertical integration, you've got to see what Vin Robotics is doing with their industrial VRH3 model. They recently demonstrated a teleoperation system that uses motion capture technology built right into a virtual reality headset. No external clunky tracking equipment needed, just the headset. This allows a human operator to control the humanoid's movements in real time, just using their natural body movements. Imagine the applications here. You could have a human safely operating a robot from miles and miles away to perform really dangerous maintenance in a hazardous environment. It's a real game changer. Moving right along to Section 4, NVIDIA's Open Platform API. Here's the thing about NVIDIA. They aren't stepping into this race to build one single finished proprietary robot. Instead, they're building the ultimate open platform. They've essentially created the ultimate cheat code foundation for the entire industry, built around the Unitree H2 reference design. Frame this in your mind as the ultimate research vessel. It's a human-scale, 6-foot, 150-pound machine built to take a beating and do demanding physical work. It has massive leg torque, a 33-pound payload capacity, and it is completely decked out with head-mounted stereo vision, wrist cameras, and motion tracking sensors. But what truly sets this physical hardware apart is this number right here. 75. That is the staggering total number of degrees of freedom this platform possesses. And a massive portion of that comes from NVIDIA pairing the robot with dual Sherpa Wave tactile 5-finger hands. Those hands add 44 degrees of freedom all by themselves. Look, getting a robot to walk is hard. Full body control is really hard. But when you add tactile 5-finger manipulation with dedicated wrist cameras, you suddenly elevate this machine into a completely new realm of complex, human-like motion. And of course, to power 75 degrees of freedom, you absolutely need this number, 270. That is the massive 270 FP4 teraflops of AI performance delivered right on board by the Jetson AGX Thor computing platform. Between the Blackwell-based GPU, the 14-core ARM CPU, and 128 gigabytes of unified memory, this robot has all the onboard processing power it needs for real-time sensor processing and AI workloads. It doesn't have to desperately ping some distant cloud server to figure out how to pick up a cup. Let's move to the software and see how this all builds together, because this is where NVIDIA's strategy truly shines. They introduced the Isaac GR00T workflow. It's 3 clean steps. Step 1, you collect demonstration data using Isaac Teleop. Step 2, you run virtual training and testing endlessly inside Isaac Sim and Isaac Lab. Step 3, you deploy those trained policies directly onto the physical robot using Isaac ROS. This end-to-end workflow is brilliant because it prevents research labs from having to stitch together random, buggy software from a dozen different vendors. It lets the engineers just focus on what actually matters: multitask AI reasoning and real-world behavior. And trust me, the industry is paying very close attention. The sheer scale of adoption here by top-tier institutions is just staggering. Places like AI2, ETH Zurich, the Stanford Robotics Center, UC San Diego, they are all completely committing to this reference design. By making this accessible to institutions that are already using platforms like the Unitree G1, NVIDIA's open reference design is rapidly cementing itself as the absolute new gold standard for robotics research worldwide. So, the crucial point is really captured perfectly by Steve Cousins, the executive director of the Stanford Robotics Center. He said, "Robotics moves fastest when researchers can build on open platforms, share code, and test ideas on real machines." That ties this whole explainer together. The isolated, siloed days of robotics where everyone was reinventing the wheel in secret, those days are ending. This global race is being accelerated by open collaboration. When labs can share their breakthroughs instantly on standardized hardware, the pace of innovation doesn't just increase, it literally goes exponential. We've seen China's split-brain architectures, we've seen Vietnam's incredibly rugged vertical integration, and we've explored America's foundational open platforms. The pieces of this giant puzzle are all coming together. So I want to leave you with this final provocative thought. As these clean lab experiments finally close the gap with our messy, unpredictable world, as advanced AI reasoning and highly realistic physical machinery perfectly align, how quickly will these robots actually step out of the research centers and completely reshape our everyday reality? I promise you, it's happening a lot faster than we think. Thank you so much for watching this explainer, and we will see you in the next one.